Our universe is a place of incredible violence and beauty. It's a vast expanse filled with wonders that boggle the mind and events that defy comprehension. Among these wonders are the stars, the luminous beacons that light up the cosmos. Stars, the building blocks of galaxies, live for billions of years. They are born from clouds of gas and dust, igniting nuclear fusion in their cores, and spend most of their lives in a delicate balance between gravity pulling inward and pressure pushing outward. But even stars don't live forever. Some die in a spectacular way, a supernova explosion. This cataclysmic event occurs when a massive star exhausts its nuclear fuel, causing its core to collapse and its outer layers to be ejected into space. These are the most powerful events we can see in the universe. The explosion releases more energy in a few seconds than our sun will emit in its entire lifetime, creating shock waves that ripple through the cosmos. And from these cosmic firestorms, neutron stars are born. These remnants are incredibly dense, with a mass greater than that of our sun, but compressed into a sphere just a few kilometers across. Imagine a star much bigger than our sun, collapsing under its own gravity. The core, once a bustling hub of nuclear reactions, is now a dense ball of neutrons. It happens in an instant. The core of the star is squeezed with unimaginable force. The density becomes so extreme that a single teaspoon of neutron star material would weigh billions of tons on Earth. Protons and electrons are crushed together. They become neutrons. This process releases a tremendous amount of energy and results in the formation of a neutron star. This is how a neutron star is created. These stellar remnants are fascinating objects, with magnetic fields trillions of times stronger than Earth's and rotation periods that can be as short as a few milliseconds. They are the incredible dense cores left behind after the most powerful explosions in the universe. A neutron star is a truly exotic object. It is essentially a giant atomic nucleus. It is made almost entirely of neutrons packed tightly together. It's like taking all the people on Earth and squeezing them into a sugar cube. This incredible density gives neutron stars some bizarre properties. They are incredibly hot with surface temperatures of millions of degrees. A sugar cube-sized piece of a neutron star would weigh billions of tons. These objects are tiny, only about 20 kilometers across, but they hold the mass of 1.5 suns. Think about the heaviest thing you can imagine. A mountain? A skyscraper? Now imagine something much denser. A teaspoonful of neutron star material would weigh as much as Mount Everest. This extreme density is almost impossible to grasp. The gravity on a neutron star is also mind-boggling. It's about 2 billion times stronger than the gravity on Earth. If you were to drop a marshmallow onto a neutron star, it would hit the surface with the force of a nuclear bomb. Neutron stars are not only incredibly dense, but they also possess the strongest magnetic fields in the universe. These magnetic fields are trillions of times stronger than Earth's magnetic field. They can warp space-time and channel jets of particles that travel at near the speed of light. These powerful magnetic fields are responsible for some of the most energetic phenomena in the cosmos. They create pulsars, which are rapidly rotating neutron stars that emit beams of radiation. These beams sweep across our line of sight like cosmic lighthouses, creating pulses of radio waves that we can detect here on Earth. Section 5. Cosmic Alchemy. Neutron stars as heavy element factories. Neutron stars play a crucial role in the universe's chemical evolution. These incredibly dense remnants of supernova explosions are not just fascinating objects of study. They are also the forges where some of the universe's heaviest elements are created. They are cosmic alchemists, forging heavy elements that are essential for life. The process begins in the heart of these stars, where extreme pressures and temperatures allow for the creation of elements that are heavier than iron. When neutron stars collide, they release tremendous energy. This cataclysmic event, known as a kilonova, is one of the most energetic occurrences in the universe. The collision generates gravitational waves and electromagnetic radiation, which can be detected across vast distances. This triggers the formation of elements heavier than iron, like gold, which are scattered into space. These elements are then incorporated into new stars, planets, and even life forms, platinum and uranium. These elements are not just rare, they are also incredibly valuable, both scientifically and economically. The platinum in your catalytic converter and the uranium used in nuclear reactors all have their origins in these cosmic events. These collisions are rare, but they are so powerful that they can seed entire galaxies with the building blocks of planets and life. The elements produced in these collisions are spread far and wide, eventually becoming part of the interstellar medium from which new stars and planets form. The gold in your jewelry, the platinum in your catalytic converter, and the uranium in nuclear reactors all owe their existence to these extraordinary cosmic events. These elements were all forged billions of years ago in the heart of a neutron star collision. The next time you look at a piece of gold jewelry or think about the elements that power our modern world, remember that they were born in the violent, beautiful collisions of neutron stars. These ancient cosmic forges have shaped the universe as we know it, providing the essential ingredients for life and the materials that drive our technology. Neutron stars, in their death throes, have given us the building blocks of our world. Section 6. Time warps, slowing down. Time's relentless march. Einstein's theory of general relativity tells us that gravity can warp time. The stronger the gravity, the slower time passes. Near the surface of a neutron star, this effect becomes extreme. Imagine two identical clocks, one on Earth and one on a neutron star. The clock on the neutron star would tick noticeably slower than the clock on Earth. Time is not absolute but is affected by the immense gravitational pull of these stellar remnants. Section 7. Cosmic Abyss, Neutron Stars versus Black Holes. Neutron stars and black holes are often mentioned together. Both are born from the death of massive stars, but they are fundamentally different objects. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. Neutron stars, while incredibly dense, are still visible to us. They emit light and other radiation. Black holes, on the other hand, are invisible. We can only detect them by their gravitational effects on surrounding matter. Section 8. When titans clash, neutron star mergers and kilonova explosions. The universe is constantly evolving. Galaxies collide, stars are born and die, and sometimes even neutron stars collide. When two neutron stars spiral towards each other, they produce gravitational waves that ripple through the fabric of space-time. The merger itself is a cataclysmic event called a kilonova. It's 1,000 times brighter than a typical supernova. Kilonovae are responsible for creating many of the heavy elements in the universe, including gold and platinum. Section 9. Neutron stars and us, the cosmic connection of life. The study of neutron stars might seem like a distant and esoteric pursuit. These incredibly dense remnants of massive stars that have exploded in supernovae are among the most extreme objects in the universe. But it has profound implications for our understanding of the universe and our place in it. By studying neutron stars, we can learn about the fundamental forces that govern the cosmos, including gravity, electromagnetism, and the strong nuclear force. These extreme objects provide unique laboratories to test the limits of physics. Neutron stars have incredibly strong magnetic fields and can spin at astonishing speeds, emitting beams of radiation that sweep across space like cosmic lighthouses. The heavy elements forged in neutron star collisions are the building blocks of planets and life itself. When these stars collide, they create conditions so extreme that new elements are formed, including gold, platinum, and uranium. The iron in our blood, which is essential for transporting oxygen throughout our bodies, the calcium in our bones, which provides structure and strength, the gold in our rings, all these elements were created in the hearts of dying stars billions of years ago. These elements were scattered across the universe when these stars exploded in supernovae, eventually becoming part of the gas and dust clouds that formed new stars, planets, and even life. We are all, in a very real sense, stardust. The atoms that make up our bodies were forged in the nuclear furnaces of stars and have traveled across the cosmos to become part of us. This cosmic connection reminds us that we are part of a vast and interconnected universe, and that our existence is tied to the life cycles of stars.